right, these are the answers to page 116. First question wants you to find the horizontal tangents to this graph. When we see horizontal tangent, it means our slope of the tangent line is 0, which means our derivative is 0. So we're going to take the derivative of this, dy dx, be 4x cubed minus 16x. Then we're going to set that equal to 0. As I do that, I'm going to factor out a 4x from both of these. So give me x squared minus 4. And then I can break that down into x plus 2x minus 2. All right, so there's three values of x that'll make this 0. They are 0, negative 2, and 2. So those are my three x values where I would have a horizontal tangent. You could put that on a graph, go y equal, and you'd see exactly those three spots are where you have the horizontal tangents. 62 is the same idea, it's just a little more difficult to execute. When we take the derivative, it's going to be square root of 3 plus 2 times the derivative of cosine, which is negative sine. So that's actually going to turn into a minus 2 sine x. Okay. Now I'm going to set that equal to 0. And what I'm going to do next is I'm going to add the 2 sine x over, and then I'll divide by that positive 2. So I get sine x equal to square root of 3 over 2. All right. And I want to know between 0 and 2 pi, when does sine equal this? So this is the opposite over hypotenuse. The angle that has an opposite of square root of 3 is 60, or pi over 3. And then sine is also positive in the second quadrant, and so I would want to have a reference angle of 60 there. That'd be 120, or double this, so 2 pi over 3. Again, a little more to that one, but it's the same concept. Take the derivative, set it equal to 0, and try to solve it. Now, 64 says, what value of k would make this function have a tangent line of this? So the key on a problem like this is to realize that the slope of this tangent line, negative 4, would equal the derivative of this function at that value, right? So I'm going to find the derivative of this. K is a constant, so its derivative is 0. And the derivative of negative x squared is negative 2x. So what we're saying is at this x value, that derivative equals negative 4. So negative 2x equals negative 4 at x equal 2. So we found the x coordinate for where this tangent line would hit. Now if I wanted the y coordinate, I could put it in the function, except I'd still have k, which I don't really know what that equals. So I'm actually going to put the 2 into the tangent line, because the tangent line and the function share that point of tangency. So if I put that in here, I get y equals negative 4 times 2 plus 7, which is negative 1. So now I know the point of tangency, 2 comma negative 1. So if I know those two values are on this function, then I can go ahead and put those in. Negative 1 will go in for the f of x. The function equals negative 1 when x equals 2. And so that means k must equal 3. Now there was quite a bit to that problem. A lot of different things that you had to know in order to move to the next part. So don't get too frustrated if you were confused on that one. 67 says, what 2 points have the greatest average rate of change? The average rate of change is the name for the slope between 2 points. So if you look at A and B, that's a pretty big slope. B and C is almost 0. C and D is a pretty big negative. D and E is a pretty flat one. I would say that between A and B, that's where I would have the greatest rate of change. And again, that's just simply the slope between this point and that point. Now they want to know, well, which is bigger, the average rate of change between A and B, or the actual instantaneous rate at B? So that means the tangent slope, right? So if you look, I've got a pretty big slope between A and B. As I get to B, it starts to flatten out because we're hitting the top of this curve. So I would say the average rate of change between A and B is greater than the instantaneous at B. Now we hit a bunch of true-false questions. And we want to really think deeply about these and have a good understanding of them. For 83, it says, if the derivative of f is equal to the derivative of g, would these be the same function? And the answer is no. I could have these derivatives be 2x and 2x, but maybe f was x squared plus 7, and maybe g was x squared minus 5. Both of those would have a derivative of 2x, but they're not the same function, so this is false. But 84 is a little different. It says, what if f is the same thing as g, except g just had a constant added to it? if we took the derivative, would we get the same thing? And the answer is yes. If I take the derivative of f, it'd be f prime. If I take the derivative of this side, it would be g prime, and then the derivative of the constant would be 0. So this is true. Number 85 wants to try to trick you here. It wants to see if you'll use a power rule. The only problem is pi is not a variable. Pi is a number, so pi squared is also a number. The derivative of the number would be 0, so this is false. The derivative would just be 0. Whereas over here, I could rewrite y as 1 over pi times x. 1 over pi would be the slope of this line then. So when we talk about the derivative would be the slope, which is 1 over pi. This is true. Over here, I've got g is equal to 3 times whatever f is. So does the derivative equal 3 times whatever the derivative is? And the answer is yeah. When you take the derivative, the constant stays. You do the derivative of the function, and you multiply it by that constant. So this is exactly how we would do it. This is true. 88, though, wants to know, if you take the derivative of this, do you just do the power rule with it down there? And we know better. We know that what we would have to do is bring that up, okay? And then we could do the derivative by going negative n x to the negative n minus 1. That's not quite what they did, so this would be false. 89 wanted to know what the average rate of change was from 1 to 2 of this function. So in other words, they want you to do f of 2 minus f of 1 over 2 minus 1. So if you put 2 into this function, you're going to get 11. Put 1 in, you're going to get 9. 11 minus 9 over 1 is equal to 2. That's the average rate of change for that function there. Okay. Now, the derivative at 1 and 2, and really the derivative anywhere, is just the slope of it. It's also 2. Okay, so it happened to be for this function, the instantaneous and the average are the same, and that's because it has a constant rate. If this had been something squared or cubed or something like that, different story. Probably would have a different value between these here. Then our last question said the volume of a cube is s cubed, and we want to know what the rate of change of that volume is here. So hopefully you thought about taking the derivative. Now, the way you would express it here is you would say the change in volume with respect to the change in the side, dv ds. And we're going to deal with that more as we move on in this chapter. But the rate of change of the volume with respect to the rate of change of s is, and then we're just using our regular power rule here. Bring the 3 down, subtract 1, we get 3s squared. So the rate of change with respect to the volume when the side equals 4, it'd be 3 times 4 squared, which is 48. And that'd be our answer. Okay. Hopefully that feels pretty comfortable. If there was a couple that got you, that can happen, but overall you hopefully feel pretty good about this.